Have you ever really thought about how a car engine works? How it turns a bit of fuel into actual motion? Well, it all boils down to one single, really elegant rule in physics. Today, we're going to demystify the first law of thermodynamics by telling the story of something super simple, just a bit of gas trapped in a box.
All right, so here's the game plan. We're going to build this idea up piece by piece. First, we'll define our little universe. Then we'll figure out how to describe it and measure the energy inside it. Once we see how that energy can change, we'll have everything we need to finally understand the first law and see how it really works.
So before we can even start talking about energy, we have to know where we're looking. In physics, the very first step is always to draw a line in the sand. You've got to decide exactly what part of the universe you're focusing on and what part is just everything else.
Now, the part we choose to study, that's called the system. And this could be anything, really. A cup of coffee, your own body, a whole planet. Everything else, literally the rest of the universe, we call the surroundings. For our story, though, we're going to keep it as simple as it gets.
So, meet our hero for today. It's this sample of gas trapped inside a cylinder with a piston that can move up and down. That gas, that's our system. The piston, the walls of the container, you, me, the air in the room, all of that is the surroundings. This super clear boundary is going to be the key to tracking where all the energy goes.
Okay, so we've got our system, but how do we describe it? If I asked you, hey, how's that gas doing? What would you even say? We need some specific terms to define its condition, or what physicists call its state. Just like you might describe a person with their height or weight, we describe our gas with a few key numbers called state variables. The big ones are its pressure, its volume, its temperature, and the one that's at the absolute heart of our story today, its internal energy. These are basically the gas's vital signs.
Let's zoom in on that last one, because it's the most important piece of the puzzle. What is this internal energy? Well, it's pretty much what it sounds like. It's all the energy that's hidden away inside the system itself. See, that gas in the cylinder isn't just sitting still. It's made of billions upon billions of tiny molecules that are constantly zipping around, bouncing off each other, hitting the walls. It's chaos in there. The internal energy, we give it the symbol U, is just the grand total of all that kinetic energy from all that frantic, random movement. And here is the absolute key connection. All that random jiggling and bouncing of molecules, well, that's exactly what we measure as temperature. So the internal energy of a gas is directly tied to its temperature. They go hand in hand. You heat the gas up, the molecules move faster, and its internal energy goes up. You cool it down, they slow down, and the internal energy drops. You can't change one without changing the other.
Okay, so our system's internal energy can change. But how does that happen? It turns out the surroundings, the outside world, can poke and prod our gas in two very specific ways to add energy in or take it out.
And here they are, side by side. First, you can literally do something mechanical, like pushing down on that piston and squeezing the gas. We call that work. Or second, you can do something thermal, like putting a flame under it. We call that heat. Both of these things, doing work on the gas or adding heat to it, are going to pump up its internal energy.
But remember, this is a two-way street. Instead of us doing work on the gas can fight back. If it gets hot and expands, it can push that piston up all by itself. When that happens, our system is doing work on the surroundings, and we can even calculate it. If the pressure doesn't change, the work it does is just that pressure, P, times the change in its volume, which we call delta V.
Okay, we've got all our pieces on the board. We've got our system with its internal energy, U, and we've got two ways for that energy to get in or out, through heat, Q, or through work, W. Now, it's time for the rule that ties it all together.
This gets us to the big question, right? How do we keep tabs on all this energy? If we add some heat, but then the system uses some energy to do work, what's the net effect? We need a way to balance the energy books.
And here it is, the first law of thermodynamics. It looks so simple, but it is unbelievably powerful. Delta U, that's the change in internal energy, is equal to Q, the heat you add, minus W, the work the system does. Honestly, this is just the law of conservation of energy in disguise. It's a fancy way of saying you can't create or destroy energy, you can only move it around or change what form it's in. This equation is our energy scorecard.
Now, to use this thing, we've got to get the plus and minus signs right. The easiest way is to think of the system's internal energy like a bank account. If Q is positive, that's a deposit. Heat is flowing into the system. If W is positive, that's a withdrawal. The system is spending energy to do work. So the change in your account balance, delta U, is just your deposits minus your withdrawals. It's really that straightforward.
Let's do a quick example. Let's say our system soaks up 800 joules of heat. That's a deposit, right? So Q is a positive 800. At the same time, it does 300 joules of work. That's a withdrawal. So W is a positive 300. So the change in its internal energy, delta U, is just Q minus W. 800 minus 300, that's 500 joules. The system's internal energy went up by 500 joules. Easy.
Okay, the real beauty of this law is how it helps us understand all kinds of different scenarios. By looking at situations where one of these terms, Q, W, or delta U, is zero, we can uncover some really neat relationships.
Well, let's look at 3 special cases real quick. First up, an adiabatic process. This just means no heat gets in or out, so Q is 0. Think about compressing the gas in an engine. It happens so fast there's no time for heat to escape. The law just becomes delta U equals negative W. Next, an isothermal process. Isothermal means constant temperature, and since temperature and internal energy are linked, delta U is 0. In this case, the law tells us Q equals W. Any heat you pump in is immediately used to do work. And finally, an isovolumetric process. Constant volume. If you lock that piston in place, the volume can't change, so no work can be done. W is 0. And the law simplifies again. Q equals delta U. Every bit of heat you add goes straight into boosting the system's internal energy.
So you can see, this one simple rule is like a Swiss Army knife. It gives us the framework to understand energy in all kinds of different situations, from a simple thermos to a roaring jet engine.
And that brings us to the really clever idea behind every engine ever made, a cyclic process. This is where our gas goes through a whole series of changes. It expands, it cools, it gets compressed, it heats up, but at the very end it returns to its exact starting point. And if it's back to its original temperature, its internal energy must be back to what it was. This means for one full cycle, the net change in internal energy, delta U, is 0. It's back to square one.
So, this leaves us with one last really cool question. If our engine can run a full cycle, get back to its starting point with its internal energy unchanged, but along the way it did useful work, right? It pushed a piston, it turned a wheel. So if delta U is 0, but W is not, where did the energy for that work actually come from? Well, the first law tells us exactly where. It had to come from Q, the net heat that we pumped into the system from burning fuel. And that right there is the secret to turning heat into motion.